Let me tell you about humanity's greatest delusion. Not religion, not love, not the idea that cryptocurrency would somehow replace actual money. No, I'm talking about the belief that we are going to colonize the galaxy. You've seen it in every science fiction movie ever made. Humanity spreading across the stars, brave explorers discovering new worlds, ancient alien civilizations waiting to share their wisdom. It's inspiring, it's hopeful. It's the ultimate expression of human ambition. It's also complete fantasy. Because here's what no one wants to admit. We are not going anywhere. Not to Alpha Centauri, not to the Andromeda Galaxy. Hell, we can barely get to Mars without everything going catastrophically wrong. And the reason isn't lack of funding or political will or technology that's just around the corner. The reason is physics. Specifically, a cosmic speed limit hardwired into the fabric of reality itself. The speed of light, 186,282 miles per second. Sounds fast, right? It's not even close to fast enough. The nearest star system to Earth, Proxima Centauri, is 4.24 light-years away. That means traveling at the speed of light, which is physically impossible, it would still take you 4 years and 3 months to get there. And that's the closest one. Most interesting stars are hundreds or thousands of light-years away. To put this in perspective, if Earth were the size of a grain of sand, the nearest star would be 4 miles away. The nearest potentially habitable planet? 40 miles. The Milky Way galaxy? About the distance from Earth to the Sun. And there are 2 trillion other galaxies beyond that. Space isn't just big. It's so obscenely, impossibly, soul-crushingly big that the human brain literally cannot comprehend it. And that size, combined with the universe's absolute refusal to let anything move faster than light, means we are essentially trapped in a cosmic prison 12 billion miles wide. Welcome to the cosmic speed limit, why we're trapped in the solar system forever. I'm going to explain why every optimistic prediction about interstellar travel is wrong, why the physics make it essentially impossible, and why, barring some miraculous breakthrough that violates everything we know about reality, humanity will die on the same rock where it was born. But hey, at least the view is nice.
Let's start by defining our prison cell. You probably think you understand how big space is. You don't. No one does. The human brain evolved to understand distances like across the savannah and to the next cave. It did not evolve to comprehend distances measured in trillions of miles. The Moon is about 238,900 miles from Earth. That's roughly the equivalent of driving around Earth's equator 10 times. The fastest spacecraft we've ever built, NASA's Parker Solar Probe, would take about 43 hours to reach the Moon at its top speed. Mars, our nearest planetary neighbor, is between 34 and 250 million miles away, depending on orbital positions. At closest approach, using current technology, the trip takes about 7 months. 7 months to reach a freezing, radiation-soaked desert with toxic soil and no atmosphere. And that's still in our cosmic backyard. Neptune, the farthest planet in our solar system, orbits at 2.8 billion miles from the Sun. Voyager 2, launched in 1977, took 12 years to reach it. 12 years to get to the edge of our own solar system, traveling at 35,000 miles per hour. And here's where it gets fun. Voyager 1, humanity's most distant object, has been traveling for over 46 years. It's currently about 15 billion miles from Earth. That's 162 times the distance from Earth to the Sun. Sounds impressive, right? It hasn't even left the solar system yet. Not really. It's passed through the heliopause, the boundary where the Sun's solar wind stops, but it's nowhere near the Oort cloud, a shell of icy objects that extends up to 2 light-years from the Sun. At Voyager's current speed, it would take 300 years to reach the inner edge of the Oort cloud, and another 30,000 years to pass through it completely. Let me repeat that. 30,000 years. That's longer than recorded human history. That's 1,500 generations. The pyramids of Giza would be built and crumble to dust 15 times over before Voyager cleared our own solar system's debris field. And then, after finally escaping the sun's gravitational influence, Voyager would need another 73,000 years to reach Proxima Centauri, the nearest star. 73,000 years to reach our closest neighbor, which is, and I cannot stress this enough, right next door in cosmic terms. So what else is out there within theoretical reach? Within 20 light-years of Earth, there are about 133 star systems. Most are red dwarfs, small, dim stars that are frankly not very interesting. A few are sun-like stars. One or two might have planets that could theoretically support life. The closest confirmed exoplanet in the habitable zone, where liquid water could exist, is Proxima Centauri b, orbiting our nearest stellar neighbor. It's about 1.17 times Earth's mass. Sounds promising. It's tidally locked, meaning one side always faces its star. It's bombarded with stellar flares. The star is a red dwarf that would make the planet's sky a perpetual deep red twilight. And, oh yeah, it's 4.24 light-years away, which we'll get to in a moment. Other potentially habitable worlds? TRAPPIST-1e, a rocky planet with Earth-like conditions, 39 light-years away. Kepler-452b, the most Earth-like planet we've found, 1,400 light-years away. Gliese 667cc, potentially in the habitable zone, 23.6 light-years away. Notice a pattern? Even the absolute closest potentially habitable worlds are measured in decades or centuries of light-speed travel. And remember, nothing with mass can actually travel at light speed. More on that nightmare in a moment. Our galaxy, the Milky Way, is about 100,000 light-years in diameter. It contains between 100 and 400 billion stars. At light speed, it would take 100,000 years just to cross from one side to the other. The galaxy's central supermassive black hole is 26,000 light-years away. The beautiful nebulae in astronomy photographs, thousands of light-years distant. The nearest major galaxy to ours, Andromeda, is 2.5 million light-years away. Even traveling at the speed of light, you'd arrive 2.5 million years after you left. For perspective, 2.5 million years ago, humans didn't exist yet. Homo habilis, one of our evolutionary ancestors, was just learning to use stone tools. And then beyond that, the observable universe is 93 billion light-years in diameter. There are an estimated 2 trillion galaxies, each containing billions or trillions of stars. The numbers are so large they become meaningless. The distances are so vast they might as well be infinite. So here's the reality. If we define local as places we could possibly reach in multiple human lifetimes using any conceivable technology, we're talking about maybe a few dozen star systems within 10 to 20 light-years. Everything else is effectively unreachable. Not hard to reach, not requires advanced technology, unreachable. And all of this assuming we could somehow travel at or near the speed of light, which brings us to the uncomfortable truth that's about to ruin your day. We can't. We can't even get close, and the laws of physics that prevent us from doing so aren't engineering challenges to be overcome. They're fundamental features of reality. In 1905, a German patent clerk with questionable hair published a paper that would destroy humanity's dreams of exploring the cosmos. His name was Albert Einstein, and he proved with mathematics so elegant and ironclad that it's never been seriously challenged that the universe has a cosmic speed limit. Nothing can travel faster than light. And here's the part that makes grown physicists weep. The closer you get to that speed limit, the more impossible it becomes to go faster. It's not a wall you can break through with enough thrust, it's an asymptote you can approach but never reach, and every incremental increase in speed requires exponentially more energy. The equation is simple. E equals mc squared. Energy equals mass times the speed of light squared. Sounds innocent enough, right? But hidden in that elegant simplicity is a cosmic screw you to anyone who wants to explore the universe. As you approach the speed of light, your mass effectively becomes infinite. To accelerate infinite mass requires infinite energy, and since there is no infinite energy source in the universe, you can't reach light speed. Period. End of discussion. Let me put this in practical terms. Our fastest spacecraft, the Parker Solar Probe, reaches about 430,000 miles per hour at its peak. That sounds insanely fast. It's 0.064% the speed of light. Not 64%, not 6.4%, 0.064%. To reach just 10% of light speed, which would still take 42 years to reach Proxima Centauri, you'd need to go more than 150 times faster than our fastest spacecraft. And the energy required doesn't scale linearly, it scales exponentially.
How much energy would it take to accelerate a spacecraft to 10% light speed? Let's say we're launching a relatively small ship, 100 tons, about the mass of the International Space Station. To reach 10% of light speed using conventional rockets, you'd need approximately 10 to the 20 joules of energy. That's 100 quintillion joules. For comparison, the total energy consumption of the entire United States in a year is about 10 to the 20 joules. You'd need to harness the entire annual energy output of America just to get one relatively small spacecraft up to 10% of light speed. And that's using perfect efficiency, which doesn't exist. Real rockets waste most of their energy as heat. Even using antimatter, the most energy-dense fuel theoretically possible, you'd need about 25 tons of antimatter reacting with 25 tons of matter to accelerate a 100-ton spacecraft to 10% light speed. Here's a fun fact. Humanity has produced about 20 nanograms of antimatter in total. Total, ever, in all of human history. We'd need 25 tons. That's 1.25 trillion times more antimatter than we've ever created. At current production rates, that would take approximately, 100 million years. Oh, and antimatter costs about $62.5 trillion per gram to produce. So your fuel cost for one starship would be roughly $1.5 quadrillion. For perspective, the entire global GDP is about $100 trillion. You'd need to spend 15 times all the money in the world just on fuel. And I haven't even mentioned the rocket equation yet. Konstantin Tsiolkovsky, a Russian scientist, derived it in 1897, and it's been crushing dreams ever since. The equation shows that the amount of fuel needed for a given change in velocity grows exponentially with that velocity change. To accelerate to high speeds, you need massive amounts of fuel. But fuel has mass, which means you need even more fuel to accelerate that fuel, which adds more mass, which requires more fuel. It's a vicious cycle that makes interstellar travel using conventional rockets essentially impossible. For every kilogram of payload you want to send to another star at 10% light speed using a conventional rocket, you'd need approximately 10 to the 15 kilograms of fuel. That's a quadrillion kilograms of fuel per kilogram of payload. The mass of Mount Everest is about 8 times 10 to the 14 kilograms. You'd need more than one Mount Everest worth of fuel for every kilogram of spacecraft. Want to send a crew of 6 with life support and habitat? That's maybe 100,000 kilograms of payload. You'd need 100 quintillion kilograms of fuel. That's approximately 1/6 the mass of the moon. Picture trying to build a rocket where the fuel tank is the size of a small moon and the payload is the size of a house. The engineering challenge isn't difficult, it's physically impossible. So conventional rockets are out. What about other propulsion methods? Ion drives use electricity to accelerate ions to high speeds, creating thrust. They're efficient but incredibly weak. The Dawn spacecraft's ion drive produced about 0.09 newtons of thrust, roughly equivalent to the weight of a piece of paper. It would take decades or centuries to accelerate to useful interstellar speeds. Nuclear pulse propulsion, the idea of detonating nuclear bombs behind a spacecraft to push it forward, was proposed in the 1950s with Project Orion. The math suggested it could reach 5 to 10% of light speed. The problems? You'd need thousands of nuclear bombs, it's banned by international treaty, the radiation would be catastrophic, and even at 10% light speed, Proxima Centauri is still 42 years away. Solar sails use photon pressure from the sun to accelerate probes. The Breakthrough Starshot initiative proposed using powerful lasers to push tiny gram-scale probes to 20% light speed. It's theoretically possible for microscopic probes, but scaling it up to carry humans? No chance. The sail would need to be thousands of miles wide, made of materials we can barely manufacture, and could only accelerate near a star. The Bussard ramjet, proposed in 1960, would scoop up hydrogen from interstellar space and use it for fusion fuel. Clever idea, fatal problems. Interstellar space is mostly empty, about 1 hydrogen atom per cubic centimeter. The magnetic scoop would need to be thousands of miles wide, and the drag from the magnetic field would cancel out most of the thrust. Every propulsion method we can imagine either requires impossible amounts of energy, impossible amounts of fuel, or impossible engineering at scales we can't achieve. And that brings us to the most fundamental problem of all.
Let's talk about why the universe hates you personally. Not humanity in general, you specifically. Because the laws of physics that prevent interstellar travel aren't just obstacles to overcome. They're built into the fundamental structure of space-time itself. When Einstein developed special relativity, he proved something profound and disturbing. Space and time aren't separate things. They're woven together into a 4-dimensional fabric called space-time. And the speed of light isn't just a speed limit for objects moving through space. It's the speed at which causality itself propagates through the universe. Nothing can travel faster than light because doing so would violate causality. You'd be able to arrive before you left. Effects would precede their causes. The universe would break. But here's where it gets weird, and by weird I mean existentially horrifying. As you approach the speed of light, time slows down for you relative to everyone else. This is called time dilation, and it's not theoretical. It's been proven with atomic clocks on airplanes and satellites. It's real. The classic thought experiment is the twin paradox. One twin stays on Earth, the other twin travels to a nearby star at 90% the speed of light and returns. When they reunite, the traveling twin has aged only a few years, while the Earth twin has aged decades. This isn't science fiction. This is what actually happens according to the mathematics of relativity, and it's been experimentally confirmed thousands of times. So let's say you somehow build a spacecraft capable of continuous 1g acceleration. That's 1 Earth gravity, which would feel like normal gravity to the crew. You could theoretically reach very close to light speed within a few years of shipboard time. Here's the math. Accelerating at 1g for about 1 year of shipboard time would get you to about 77% of light speed. After 2 years, you'd reach 97%. After 3 years, 99.5%. You'd asymptotically approach but never reach light speed. Sounds great, right? You could reach Proxima Centauri in about 5 years of your subjective time. The problem? Back on Earth, more than 6 years would pass. By the time you reached even a moderately distant star, say 100 light-years away, you'd experience about 12 years of shipboard time. But on Earth, more than 100 years would pass. Your children would be dead. Your grandchildren would be dead. Everyone you knew would be long gone. If you had a mission to report back findings, there'd be no one left who remembered sending you. The civilization that launched you might not even exist anymore. And this is why all those science fiction stories about galactic empires are nonsense. You can't maintain a civilization across light years of space when every interstellar journey is a one-way trip into the far future. There's no commerce, no communication, no coherent political structure. every colony world would be isolated by decades or centuries of communication lag. Speaking of communication, even if you could somehow travel to another star, you couldn't talk to anyone back home. Light signals travel at light speed. A message to Proxima Centauri takes 4.24 years to arrive. The response takes another 4.24 years. That's an 8.5-year round trip for a simple hello. At 10 light years, it's a 20-year conversation delay. At 100 light years, it's 200 years. Want to ask Earth for help with a critical engineering problem? Better hope your descendants' descendants can figure it out, because the answer won't arrive in any living person's lifetime. But wait, there's more. Time dilation isn't the only relativistic effect. There's also length contraction. As you approach light speed, distances in your direction of travel literally shrink. At 90% light speed, they contract to about 44% of their rest length. At 99% light speed, they contract to 14%. From the perspective of a spacecraft traveling at 99.99% light speed, the distance to Proxima Centauri wouldn't be 4.24 light years, it would be about 0.06 light years. You could theoretically cross it in about 22 days of shipboard time. But here's the nightmare part. Those contracted distances only apply to you. The rest of the universe still experiences the full distance and time. You might experience only days or weeks of travel, but back on Earth, years or decades pass. You're essentially time traveling into the future whether you want to or not. And we still haven't addressed the mass problem. As you approach light speed, your relativistic mass increases towards infinity. This isn't some abstract mathematical concept. It's a real physical effect that makes acceleration harder and harder. At 90% light speed, your relativistic mass is about 2.3 times your rest mass. At 90%, it's about 7 times. At 99.99%, about 71 times. At 99.999%, about 707 times. This means the energy required to accelerate doesn't just increase linearly, it goes asymptotically vertical as you approach light speed. Going from 90% to 95% light speed requires more energy than going from 0 to 90%. Going from 90% to 99.9% requires more energy than going from 0 to 99%. Let's put real numbers on this. To accelerate a 1,000-ton spacecraft, about 10 times the mass of the ISS, to various speeds, 10% light speed, about 10 to the 20th joules, the entire US annual energy output. 50% light speed, about 10 to the 21 joules, 10 times US annual energy. 90% light speed, about 10 to the 22 joules, world energy output for a century. 99% light speed, more than the sun outputs in an entire day. 99.99% light speed, more than the sun outputs in an entire week. To get a single spacecraft up to speeds where interstellar travel becomes feasible in human lifetimes, you need to harness energy comparable to a star. Not a lot of energy, not more than we currently use, star-level energy output. The Kardashev scale measures civilizations by their energy use. Type 1 can harness all the energy hitting their planet. Type 2 can harness all the energy from their star. Type 3 can harness all the energy from their entire galaxy. We're currently about 0.73 on the Kardashev scale. We're not even a Type 1 civilization yet. And to engage in regular interstellar travel, we'd need to be well into Type 2. We'd need to build structures like Dyson swarms, massive arrays of solar collectors surrounding the sun, capturing significant fractions of its total energy output.
The amount of material needed for a Dyson swarm? Approximately the mass of Jupiter. The engineering challenge? Disassembling a gas giant planet and converting it into billions of orbital platforms. The time required? Centuries or millennia, even with exponentially advancing technology. And that's assuming it's even possible, because here's a fun realization. Every megastructure, every advanced propulsion system, every way to cheat the speed of light that science fiction has invented, all of them require exotic physics that probably doesn't exist. Our understanding of physics is encoded in the standard model of particle physics and Einstein's theory of general relativity.
These theories have been tested to absurd precision. Every prediction has been confirmed, every experiment supports them, and both theories unequivocally state that faster-than-light travel is impossible. We've built particle accelerators that slam particles together at 99.9999% the speed of light. We've never observed anything traveling faster than light. Not once, not ever. Every single time we test the speed limit, the universe confirms it's real. Cosmic rays, high-energy particles from space, reach speeds of 99.999999999% the speed of light. That's 11 nines. They're moving as fast as anything in the universe can move, and yet they still can't break the light barrier. Some physicists have speculated about tachyons, hypothetical particles that move faster than light, but tachyons have never been observed, would require imaginary mass, yes, really, and would violate causality. They almost certainly don't exist, and even if they did, we'd have no way to use them for propulsion. In 2011, researchers at CERN claimed they'd detected neutrinos traveling faster than light. The physics community went insane for about 6 months. Then they found the error, a faulty cable connection in the timing system. The neutrinos were actually traveling at normal speeds, slightly below light speed, exactly as relativity predicted. The universe doesn't grant exceptions. The speed limit is absolute. And even if you could somehow reach relativistic speeds, you'd face another problem. At those speeds, every hydrogen atom in interstellar space becomes a high-energy cosmic ray. Space dust becomes armor-piercing bullets. A collision with something the size of a grain of sand would release energy equivalent to several tons of TNT. You'd need shielding meters thick, made of exotic materials, adding enormous mass to your spacecraft, which requires more energy to accelerate, which requires more fuel, which adds more mass. We're back to the tyranny of the rocket equation. Even micrometeorites would erode your spacecraft over time. The interstellar medium isn't empty. It contains about 1 atom per cubic centimeter. At 90% light speed, those atoms hit with enough energy to gradually ablate any surface material. Your spacecraft would slowly be sandblasted away during the journey. And let's not forget radiation. Space is filled with cosmic rays, high-energy particles from supernova explosions, black holes, and other violent cosmic events. At Earth, our magnetic field and atmosphere protect us. In interstellar space, there's no protection. A crewed spacecraft would need heavy shielding against galactic cosmic rays, but heavy shielding means more mass, which means more energy, which means you get the idea. The mass-energy propulsion problem is inescapable. Even if you solve the propulsion, energy, shielding, and life support problems, you still need life support for a multi-year or multi-decade journey. Food, water, oxygen, waste recycling. We've kept humans alive on the ISS for up to a year. A journey to even the nearest stars would take decades or centuries, so you'd need a generation ship, a massive vessel carrying hundreds or thousands of people with the expectation that their descendants would complete the journey. You'd need perfect recycling systems, sustainable food production, genetic diversity to prevent inbreeding, and a stable social structure that could survive for decades in a closed environment. We can't even keep small groups of people in enclosed environments on Earth for a few years without psychological problems. Biosphere 2, an experiment in the 1990s where 8 people lived in a sealed environment for 2 years, nearly ended in disaster. Conflicts erupted. The environment became toxic. It was declared a failed experiment. Antarctic research stations, isolated for months during winter darkness, report high levels of psychological stress, depression, and interpersonal conflict. And those people know they're going home eventually, can communicate with the outside world, and can be evacuated in emergencies. Now imagine a generation ship. You're born on a spacecraft, will die on a spacecraft, and your children and grandchildren will never see the destination. You have no option to leave, no emergency escape, no communication with Earth that isn't decades delayed. The psychological challenges would be immense. Science fiction loves generation ships, but rarely addresses the social dynamics realistically. What happens when the third generation decides they don't want to continue the mission? What if they turn the ship around? What if there's a mutiny? What if the social structure collapses into authoritarianism to maintain order? And even if everything goes perfectly, if you solve the propulsion, energy, shielding, life support, and social problems, you still arrive at an alien world that's probably hostile to human life. Most exoplanets are nightmares. Too hot, too cold, wrong atmospheric composition, crushing gravity, toxic chemicals, intense radiation, no magnetic field, tidally locked, orbital instability. The list goes on. We talk about terraforming Mars, a planet in our own solar system, where a day is roughly 24 hours, gravity is only 38% of Earth's, and conditions are relatively well understood. The estimated cost is tens of trillions of dollars, and the timeline is centuries or millennia. And that's the easy case. Mars is next door. An exoplanet tens of light years away? You'd arrive with no real-time data about current conditions, no infrastructure from home, and no way to evacuate if things go wrong. You'd be committed to making it work or dying trying. This is the reality of interstellar travel. It's not hard, it's not expensive, it's not a few breakthroughs away. It's functionally impossible.
Okay, let's say you're stubborn. You refuse to accept that physics has destroyed your dreams. Let's actually try to engineer a realistic starship. Let's see exactly where this fantasy falls apart. First question, what kind of propulsion? We've already established that chemical rockets are useless, ion drives are too weak, and nuclear pulse propulsion is insane. So what's left? The most promising concept is fusion propulsion. Fuse hydrogen into helium, like the sun does, and use the energy for thrust. Fusion releases enormous energy, about 0.7% of the mass energy content, compared to chemical rockets at 10 to the minus 10th percent. That's 7 trillion times more energy per kilogram. There is just one tiny problem. We can't do it. Not at useful scales. Not yet. We've achieved fusion in laboratories and thermonuclear weapons, but sustained, controlled, net-positive fusion propulsion doesn't exist. The International Thermonuclear Experimental Reactor, ITER, is a massive fusion research project that's been under construction since 2007. Current completion estimate? 2035. Costs so far? Over $22 billion. And ITER is a test reactor. It's not designed to produce power for a grid, let alone propel a spacecraft. Even if we perfect fusion propulsion, the exhaust velocity would be maybe 3 to 5% the speed of light. That sounds good until you do the math. To reach 10% light speed, you'd still need an enormous mass ratio. Fuel would still be a massive fraction of your total ship mass. What about antimatter? It's the ultimate fuel, 100% mass-to-energy conversion. 1 kilogram of antimatter reacting with 1 kilogram of matter releases 1.8 times 10 to the 17th joules. That's about 43 megatons of TNT equivalent. The energy density is unmatched. Here's the problem. Making antimatter is absurdly inefficient. At CERN, producing 1 gram of antimatter would take about 100 billion years using current technology and consume more energy than Switzerland uses in a year. The production cost is about $62.5 trillion per gram. And even if you could produce it affordably, storing antimatter is nightmarishly difficult. It annihilates instantly upon contact with normal matter. You'd need magnetic containment systems with 100% reliability, because a containment failure on a ship with tons of antimatter would be, well, imagine a multi-megaton thermonuclear explosion inside your spacecraft. So let's design our starship with conservative assumptions. We'll aim for 10% light speed, which makes Proxima Centauri a 42-year journey. We'll use advanced fusion propulsion. We'll assume a crew of 100 people for genetic diversity. Let's figure out what we need. Life support. Each person needs about 2 kilograms of food, 3.5 liters of water, and 0.8 kilograms of oxygen per day. For 100 people over 42 years, about 15,330 days, that's food, 3 million kilograms, 3,000 tons, water, 5.4 million liters, 5,400 tons,
Oxygen, 1.2 million kilograms, 1,200 tons. Total, 9,600 tons just for consumables. Of course, you'd recycle everything. Water can be purified and reused, waste can be processed, oxygen can be regenerated from CO2, but recycling is never 100% efficient. You'll maybe lose 1 to 5% per cycle. Over 42 years, that compounds. You'd probably grow food on board, hydroponics or aeroponics. That requires space, lighting, nutrients, and system redundancy. Add another 500 to 1,000 tons for the agricultural infrastructure. Habitat space. NASA recommends minimum 25 cubic meters per person for long-duration missions. For 100 people, that's 2,500 cubic meters of living space. Doesn't sound too bad until you factor in structural mass. The ISS has about 388 cubic meters of pressurized volume and weighs about 420 tons. Scaling that up, your habitat modules would weigh at least 3,000 tons, and that's before adding radiation shielding. Shielding against galactic cosmic rays requires several meters of material: water, polyethylene, or metal. A sphere with 20-meter radius, big enough for 100 people, would need a shell 3 to 5 meters thick. Using water as shielding, which is effective and can be used for life support, you'd need approximately 15,000 tons of water just for radiation protection. Propulsion system: fusion reactor, fuel tanks, magnetic nozzles, and heat radiators. Even with optimistic assumptions, you're looking at 5,000 to 10,000 tons of hardware. Power generation for life support, computers, lighting, and other systems. The ISS uses about 120 kilowatts. Scale up for 100 people and a 42-year mission, you'd need robust, redundant power systems, nuclear reactors, solar panels, useless in deep space, or fusion reactors, another 1,000 to 2,000 tons. Let's tally it up. Life support and consumables, 10,000 tons, habitat, 3,000 tons, radiation shielding, 15,000 tons, propulsion systems, 7,000 tons, power systems, 1,500 tons, margins and redundancy, 5,000 tons. Total spacecraft dry mass, approximately 41,500 tons. Now, how much fuel? Using the rocket equation and assuming advanced fusion propulsion with an exhaust velocity of 3% light speed, to accelerate 41,500 tons to 10% light speed, you'd need approximately 95,000 tons of fuel. Total launch mass, 136,500 tons. That's about 325 times the mass of the ISS. For comparison, the Saturn V rocket could lift 140 tons to low Earth orbit. You'd need to launch 975 Saturn V equivalent rockets just to get the components into orbit, then assemble them in space. Cost estimate? The ISS cost about $150 billion and took 13 years to build with international cooperation. Your Starship is 325 times larger and far more complex. Conservative estimate? $50 trillion to $100 trillion. That's half the global GDP to 1 times the global GDP. Construction time? Even with massively scaled-up space manufacturing, you're looking at 50 to 100 years minimum. By the time you finish building the ship, the original mission planners would be dead. And remember, this gets you to Proxima Centauri in 42 years. That's 42 years of hoping nothing breaks catastrophically, because there's no repair shop at the midpoint. Every system has to work perfectly for 4 decades. If something fails, a critical reactor component, a life support processor, a computer system, your crew dies. You'd need 3 or 4 times redundancy for every critical system, which increases mass, which requires more fuel, which increases mass. The engineering margins have to be absurdly conservative because failure is not an option. Communication. Earth is getting farther away every second. After 1 year, you're about 0.1 light years away. Messages take 36 days each way. After 10 years, about 1 light year away. 1 year each way for messages. By the time you're halfway to Proxima Centauri, communication delays are 2+ years each direction.
Navigation. At 10% light speed, you're covering about 18 million miles per hour. At that speed, hitting something the size of a pebble releases energy equivalent to 50 tons of TNT. You need real-time collision avoidance for objects that might be impossible to detect until it's too late. And you can't steer quickly at those speeds. Changing course requires braking and re-accelerating, which burns fuel you don't have to spare. Your trajectory has to be perfect from the start, which requires knowing exactly where Proxima Centauri will be 42 years in the future. Stellar motion and gravitational perturbations make this calculation incredibly complex. Let's say everything goes perfectly. You survive the journey. You arrive at Proxima Centauri. Now what? You're traveling at 10% light speed. You need to slow down or you'll shoot right past your destination. Deceleration requires just as much fuel as acceleration, except we didn't budget for deceleration fuel. Oops. To carry enough fuel to brake, you'd need to double your fuel load. That increases launch mass to about 227,000 tons. Now you need 1,621 Saturn V's equivalent launches. Cost increases to $100 to $200 trillion. Alternatively, you could try gravitational braking, using the target star's gravity to slow down. But that requires precise trajectory planning and might take years or decades of swooping maneuvers. And if you miscalculate, you either crash into the star or fling yourself off into deep space with no way to recover. Assuming you successfully brake into the system, you now need to identify a destination planet, reach it, and enter orbit. That requires more fuel, more time, and perfect execution. If the planet has an atmosphere, you need heat shields and landing systems. If it doesn't, you need fuel for a powered landing. Either way, you're adding more mass to the original spacecraft design, which compounds all the earlier problems. And once you land, you need to survive. That means habitat construction, food production, water extraction and purification, power generation, manufacturing capabilities, medical facilities, and communication systems. All of that equipment adds mass to your spacecraft. Every kilogram of settlement equipment is another kilogram you have to accelerate to 10% light speed and decelerate at the destination. And there's no return journey. You don't have fuel for a trip back. Even if you did, everyone you knew on Earth would be dead or elderly by the time you returned, minimum 84 years round trip, plus however long you spent at the destination. This is a one-way trip. Everyone on board knows they'll die on an alien world, assuming they even survive the journey and landing. It's not exploration, it's exile. Who volunteers for that? You'd need 100 people willing to leave Earth forever, knowing they'll spend 42+ years in a cramped spacecraft, arriving at a world that might be uninhabitable with no possibility of rescue or return. The psychological screening alone would disqualify most candidates. You'd need people who are highly skilled, engineers, scientists, doctors, physically healthy, psychologically stable, willing to leave everyone they know forever, able to function in extreme isolation, and genetically diverse enough to found a viable population. And 100 people is barely enough genetic diversity to avoid inbreeding problems. You'd really want 500 to 1,000 people, which multiplies all the mass, fuel, and cost calculations by 5 to 10x. So here's the bottom line. Even with optimistic assumptions about future technology, a realistic crewed interstellar mission requires tens to hundreds of trillions of dollars, decades or centuries to build, 136,000 to 500,000 tons of spacecraft, technology that doesn't yet exist, fusion propulsion, perfect life support, 100 to 1,000 people willing to exile themselves forever, acceptance that everyone involved will likely die before success. For perspective, the Manhattan Project cost $28 billion in today's money. The Apollo program cost $280 billion. The International Space Station cost $150 billion. Those were all considered absurdly expensive at the time. A crewed interstellar mission would cost hundreds of times more than the most expensive project in human history, would take longer to build than most nations have existed, and would have near zero chance of success. Nobody's funding that. Not corporations, not governments, not international coalitions. The return on investment is zero. The economic benefit is zero. The strategic value is zero. It's not that interstellar travel is hard, it's that interstellar travel makes no sense. Which brings us to the desperate fantasies, the exotic physics and speculative technologies that science fiction writers and optimistic futurists cling to, the loopholes, the workarounds, the maybe if we just scenarios. Spoiler alert, they don't work either.
This is the part where I crush your remaining dreams, because I know what you're thinking. Sure, conventional physics makes interstellar travel impossible, but what about warp drives, wormholes, quantum teleportation, all those cool things from Star Trek and Stargate? Yeah, about that. Let's talk about why every science fiction shortcut is either impossible, requires physics that doesn't exist, or demands energy sources we could never harness. First up, the Alcubierre drive, also called a warp drive. In 1994, physicist Miguel Alcubierre published a paper showing that mathematically you could warp space-time to create a bubble that moves faster than light without technically violating relativity. The idea is elegant. Compress space-time in front of your ship and expand it behind you. You're not moving through space, you're moving space itself. The ship stays stationary inside the bubble while the bubble moves faster than light. Technically, you're not breaking the speed limit because you're not actually moving. Here's the problem. To create this space-time distortion, you'd need negative energy. Not a lot of energy, not more energy than we currently have, negative energy. Now, negative energy does exist in quantum mechanics, sort of. The Casimir effect demonstrates negative energy densities between two close parallel plates in a vacuum. It's real, measurable, and completely understood. The problem is scale. The Casimir effect produces unimaginably tiny amounts of negative energy. We're talking nanoscale forces measured in micronewtons. To power an Alcubierre drive, you'd need negative energy equivalent to the entire mass energy of Jupiter. That's not difficult to produce, we have no theoretical framework for how to produce it. It would require exotic matter that probably doesn't exist anywhere in the universe. And even if it did exist, we'd need to harvest an entire planet's worth of it. Subsequent research tried to reduce the energy requirements. In 2012, Harold White at NASA proposed modifications that could theoretically reduce the energy needed to the equivalent of the Voyager 1 spacecraft's mass, about 700 kilograms. Still requires negative energy, which we can't create, still requires exotic matter, which probably doesn't exist, still requires technology so far beyond our capabilities that it might as well be magic. And there's another problem. Warp drives might violate causality. Some physicists have shown that Alcubierre-like solutions to Einstein's equations would allow closed time-like curves, time travel to the past, and time travel creates paradoxes that physics doesn't allow. Stephen Hawking proposed the chronology protection conjecture, the idea that the laws of physics prevent time travel paradoxes. If warp drives enable time travel, the universe probably has some mechanism to prevent them from working. Plus, recent calculations suggest that as an Alcubierre drive accelerates, particles would accumulate at the edge of the warp bubble. When you decelerate, those particles would be released as an enormous burst of radiation, potentially enough to sterilize your destination planet. So, warp drives, mathematically interesting, physically impossible, and potentially catastrophically dangerous even if you could build one. Cross that off the list. What about wormholes? Einstein's field equations allow solutions where space-time is connected through a shortcut, a tunnel connecting two distant points. Travel through the wormhole and you arrive at your destination instantly. Again, the math works. Einstein-Rosen bridges, traversable wormholes, are valid solutions to general relativity. The problem is, once again, exotic matter. Natural wormholes, if they exist at all, would collapse immediately. To keep a wormhole open and stable for something as massive as a spacecraft to pass through, you'd need enormous amounts of exotic matter with negative energy density threaded through the throat of the wormhole. How much exotic matter?
Estimates vary, but we're talking about mass energy equivalent to stars or even galaxies, depending on the size of the wormhole. You'd need to manipulate energies at scales where quantum effects and general relativity interact, a regime where we don't even have a complete theory. And that's assuming wormholes can be created artificially. Natural wormholes, if they exist at all, would be quantum scale, far smaller than a proton, and would exist for infinitesimally brief moments. Expanding one to macroscopic size would require, well, we have no idea. It might be impossible even in principle. Plus, you'd need to position one mouth of the wormhole at your destination, which means you need to get it there by conventional means first. You'd have to transport one wormhole mouth to Proxima Centauri at subluminal speeds, which takes decades or centuries just to set up your shortcut. It doesn't actually solve the travel problem. And wormholes are inherently unstable. Any perturbation, like, say, a spacecraft trying to pass through, might collapse the wormhole, destroying the spacecraft and releasing catastrophic amounts of energy. You'd be gambling your life that the structure holds together during transit. Oh, and wormholes also enable time travel and closed time-like curves. Chronology protection conjecture probably prevents them from being traversable for the same reason that warp drives from working. Wormholes, theoretically possible, practically impossible, require physics and technology we don't have, and probably violate causality. Next, what about quantum teleportation? Particles can be entangled. Their quantum states become correlated. Measure one and you instantly know the state of the other, even if they're light years apart. Doesn't that violate the speed of light? No. Quantum entanglement doesn't transmit information faster than light. You can't use entanglement to send messages or teleport objects. The correlations are only revealed when you compare measurements through a classical communication channel, which is limited to light speed. Quantum teleportation does exist, but it's not what science fiction makes it seem. You can transfer the quantum state of one particle to another distant particle using entanglement, but you destroy the original particle, you need a classical communication channel to complete the transfer, you can't teleport anything larger than individual particles, you can't teleport information faster than light. Teleporting a human would require measuring and transmitting the quantum state of every particle in your body, approximately 10 to the 28th atoms. The amount of information is beyond astronomical. The Heisenberg uncertainty principle means you can't measure all properties simultaneously, and disassembling a human at the quantum level would kill them instantly. Quantum teleportation, real, but useless for interstellar travel. Moving on. What about hyperspace, subspace, or other alternate dimensions where the speed of light is different or doesn't apply? Zero basis in physics. String theory does predict extra dimensions, possibly 10 or 11 total space-time dimensions, but these extra dimensions are either compactified to Planck scale sizes, 10 to the negative 35th meters, or are theoretical constructs that don't correspond to physical space you could navigate through. There's no evidence for accessible alternate dimensions where different physical laws apply. It's pure speculation, unfalsifiable, and has no mathematical or experimental support.
So if exotic physics won't save us, what about slow boat approaches? Generation ships, suspended animation, seed ships. Cryogenic suspension, we can't do it. We can cool people to near-death temperatures and revive them in the short term, but long-term vitrification of humans causes irreversible cellular damage. Every cryonics company is banking on future technology to revive their clients. It's not proven, it's not reliable, and it might be fundamentally impossible. Even if you could suspend crew members, you'd still need active systems to maintain the ship, repair damage, monitor course, and wake people at the destination. Those systems have to work perfectly for decades without human intervention. Good luck with that. Seed ships, sending frozen embryos and artificial wombs to grow humans at the destination, have different problems. Who raises the children? AI? That's assuming we develop human-level AI that's also a good parent, which is wildly optimistic. The first generation would grow up without human contact, likely developing severe psychological problems. What about uploading consciousness to computers and sending digital minds?
That assumes consciousness can be uploaded, which is philosophically and technically unproven. We don't understand consciousness well enough to know if it's substrate independent. And even if you could upload minds, are they still you, or just copies while the original dies? Von Neumann probes, self-replicating machines that spread across the galaxy, building copies of themselves at each star system. Interesting idea, except we can't build self-replicating machines at that scale. Uncontrolled replication could strip mine the galaxy, the gray goo scenario. It doesn't help humans travel, it just spreads robots. It takes millions of years to spread across the galaxy, even at high speed. All of these approaches still require becoming a Type 2 civilization, harnessing energy at stellar scales. We're nowhere close. Our total global energy consumption is about 10 to the 20 joules per year. The sun outputs 10 to the 26 joules per second. We use in a year what the sun produces in less than 1 second. Building a Dyson swarm to capture solar energy requires disassembling planets, building trillions of orbital collectors, and managing them for centuries. Even with exponential technological growth, this is centuries or millennia away, if it's possible at all. And building such megastructures require resources we don't have easy access to. Mercury has only 3.3 times 10 to the 23 kilograms of mass. A full Dyson swarm might require 10 to the 20 to 10 to the 22 kilograms of material, depending on design. You'd need to disassemble multiple planets. Optimistic projections suggest we might achieve Type 2 status in 1,000 to 3,000 years, assuming continuous exponential growth in energy production. That's assuming no collapse, no major wars, no resource depletion, and perfect technological progress. And here's where it gets philosophically dark. If interstellar travel were possible with achievable technology, we should see evidence of alien civilizations that figured it out. The Fermi paradox asks, where is everybody? We've found no signs of alien megastructures, no interstellar probes visiting our solar system, no radio signals from extraterrestrial civilizations. The galaxy seems empty, at least of advanced technological civilizations. One explanation is the Great Filter, some barrier that prevents civilizations from spreading across the galaxy. Maybe that filter is ahead of us. Maybe it's the impossibility of interstellar travel. Maybe every intelligent species eventually does the math, realizes they're trapped on their home world, or at most in their home solar system, and either accepts that limitation or goes extinct trying to overcome it. Here's a sobering thought. If we devoted 10% of global GDP, $10 trillion per year, to developing interstellar travel technology and maintained that investment for 100 years, we'd spend $1 quadrillion. That might be enough to send a handful of probe missions to nearby stars. Maybe. The return on that investment? Scientific data from a handful of star systems arriving decades after the probes reach their destinations. No economic benefit, no strategic advantage, no practical applications. What could we do with $1 quadrillion spent on Earth instead? Solve climate change, end poverty, cure diseases, build sustainable infrastructure, advance technology, explore the oceans, develop fusion power? Tangible benefits that improve life for billions of people. Is it ethical to spend trillions on interstellar vanity projects when that money could save millions of lives and prevent immense suffering? The answer is pretty clearly no. Space exploration advocates argue that inspiring goals drive technological development with spillover benefits. That's true. NASA's budget has returned value through technological innovations, but there's diminishing returns. Spending billions on Mars missions might be justified. Spending trillions on interstellar missions that won't succeed in our lifetimes? Probably not. The opportunity cost is too high. So, here we are. The physics prevents faster-than-light travel. The engineering makes slower-than-light travel absurdly expensive and dangerous. The economics make it unjustifiable. The timescales make it irrelevant to anyone alive today. Interstellar travel isn't impossible the way perpetual motion is impossible.
It's impossible the way building a bridge across the Pacific Ocean is impossible. You could theoretically do it, but the cost-benefit analysis makes it absurd to attempt. We're trapped, not by lack of imagination, not by insufficient technology, not by political barriers. We're trapped by the fundamental structure of space-time itself.
So let's talk about acceptance. Not the fun kind where you accept your limitations and then overcome them through determination. The hard kind. The kind where you realize the universe doesn't care about your dreams and you're going to die on this rock no matter what. Our accessible territory is the solar system, about 12 billion miles across if you count the heliopause, about 200,000 astronomical units if you count the Oort cloud. Sounds big, right? The Milky Way is about 100,000 light-years in diameter. That's approximately 600 million times wider than our solar system. We have access to 0.00001% of our galaxy's volume, and that's before considering the other 2 trillion galaxies. In cosmic terms, humanity's sphere of influence is invisibly small. We're microbes on a dust speck, telling ourselves stories about conquering the universe. Here's what our future actually looks like. We'll probably establish bases on the moon, maybe build habitats on Mars, though that's questionable given the enormous costs and limited benefits. We might mine asteroids for resources. We could build space stations at Earth-Sun Lagrange points, possibly establish colonies in the asteroid belt or moons of Jupiter and Saturn. That's it. That's the extent of human expansion for the next few centuries, possibly ever. The inner solar system, maybe the asteroid belt, potentially the moons of the outer planets if we're ambitious and lucky. But Neptune, Uranus, the Kuiper belt, the Oort cloud, the distances and conditions make them effectively inaccessible. Neptune is 2.8 billion miles away. The Oort cloud is 1,000 times farther. What's the point? There's nothing there worth the trouble. Space colonization only makes economic sense if there's a return on investment. The moon might have helium-3 for fusion reactors if we ever perfect fusion. Mars has what? Red dirt? Low gravity? Radiation? The asteroids have metals, but extraction and transport costs might exceed their value. Every space colony would require massive, ongoing support from Earth. Self-sufficient colonies are science fiction. The capital costs are enormous, the operating costs are perpetual, and the economic output is negligible or zero. And here's the uncomfortable truth. Earth is astonishingly, amazingly, uniquely well-suited to human life. We evolved here. The temperature, gravity, atmosphere, water, radiation protection, magnetic field, food sources, everything is perfect for us. Every other planet is hostile. Mars is a frozen, radiation-soaked desert. Venus is a sulfuric acid hellscape with crushing pressure and 900 degrees Fahrenheit temperatures. Mercury is tidally locked with 800 degrees dayside and negative 290 degrees nightside. The outer planets are gas giants with no solid surface and crushing gravity. The moons? Europa has a subsurface ocean buried under miles of ice in the intense radiation field of Jupiter. Titan has liquid hydrocarbon lakes at negative 290 degrees Fahrenheit with no oxygen. Enceladus might have hydrothermal vents under miles of ice around a tiny moon with negligible gravity. Terraforming? We can't even manage Earth's climate, and we're destroying the one planet perfectly suited for us. The idea that we'll terraform Mars, turning a dead world into a living one over centuries or millennia, is pure fantasy, when we can't even prevent climate change at home. Maybe we need to reframe our thinking. Instead of humanity will spread across the galaxy, maybe we should think humanity will learn to thrive sustainably on one planet for millions of years. Because here's another sobering fact. Most civilizations don't last very long. The Roman Empire lasted about 1,000 years. the Egyptian civilization about 3,000 years. Modern industrial civilization is only about 250 years old. We're infants in civilizational terms. And we face existential threats: climate change, nuclear weapons, bioweapons, AI risks, resource depletion, ecological collapse. The statistical likelihood of human civilization surviving another 1,000 years is uncertain. Another 10,000 years? Another million? Given that reality, maybe our priorities should be survive on Earth, build sustainable systems, prevent extinction, create a stable, long-lasting civilization that doesn't destroy itself or its environment. If we achieve that, we can cautiously expand into the solar system, use space resources to support Earth, build orbital habitats with artificial gravity, create redundancy so a single planetary disaster doesn't wipe us out. Gerard K. O'Neill proposed enormous rotating space habitats, cylinders several miles long that generate gravity through rotation. With enough resources and infrastructure, you could house millions of people in O'Neill cylinders throughout the solar system. That's a plausible future. Billions on Earth, millions in space habitats and colonies, robust industry utilizing asteroid resources, sustainable energy from fusion or solar satellites. Not glamorous, not galaxy-spanning, but realistic and achievable within centuries. What about contact with alien civilizations? If interstellar travel is impossible, maybe communication is the solution. SETI, the search for extraterrestrial intelligence, has been listening for alien radio signals since the 1960s. Results so far: nothing confirmed. We've detected some interesting signals, like the famous WOW signal in 1977, but nothing repeatable or definitively artificial. And communication faces the same light speed limitation. A message to Proxima Centauri takes 4.24 years. A reply takes another 4.24 years. That's an 8.5-year conversation delay for the nearest star. But for more distant civilizations, the delay becomes generations. Send a message to a civilization 100 light-years away, and your great-great-grandchildren might receive a reply. Build a meaningful relationship or exchange of ideas? Forget it. But maybe that's okay. Even one-way communication, receiving evidence that we're not alone, would be profound. Detecting alien technology or receiving an alien message would answer one of humanity's biggest questions. And if we never detect anyone, that's profound too. It means either life is extremely rare, intelligence is extremely rare, technological civilizations destroy themselves quickly, or interstellar communication is so difficult that no one bothers. The rare Earth hypothesis suggests complex life requires such specific conditions: right star type, right planetary mass, right orbit, large moon, magnetic field, plate tectonics, Jupiter-like protector planet, no nearby supernovae, stable climate. That Earth-like worlds are extraordinarily rare. Maybe the galaxy is full of planets with microbial life, but complex multicellular life is vanishingly rare. Maybe we're one of the few worlds that got lucky enough to develop intelligence. If that's true, we have a responsibility, not to spread across the galaxy, we can't, but to survive, to preserve life, to be stewards of the rare and precious thing that arose on Earth. The universe will outlast us by trillions of years. Stars will burn out, galaxies will drift apart due to cosmic expansion. Eventually, heat death will claim everything. In the long run, nothing we do matters.
But on human timescales, everything we do matters. We can reduce suffering, increase well-being, create beauty, expand knowledge, preserve biodiversity, build sustainable systems. Our legacy might not be colonies among the stars. It might be knowledge, understanding the universe deeply, even if we can't physically explore most of it. Sending information, humanity's accumulated wisdom, encoded in electromagnetic signals or physical artifacts, just in case someone finds them someday. We've already done this. The Voyager spacecraft carry golden records with sounds and images from Earth, humanity's message in a bottle, drifting through interstellar space for billions of years. It's probably futile. The odds of anyone finding those records are infinitesimally small, but there's something beautiful about the gesture, humanity acknowledging its cosmic loneliness and still reaching out just in case. So, here we are, trapped on a tiny planet orbiting an ordinary star in an unremarkable region of a galaxy containing billions of stars in a universe of trillions of galaxies. The distances are impossible, the physics is unforgiving, the economics don't work. We're never going to explore the galaxy. We're never going to meet alien civilizations face to face. We're never going to see Earth-like worlds orbiting distant suns with our own eyes. But maybe that's okay. Maybe the meaning of human existence isn't about conquering the cosmos. Maybe it's about thriving where we are, appreciating the staggering improbability of our existence, recognizing that on this one small world, life emerged, evolved complexity, developed consciousness, and began asking questions about the universe. We're the universe becoming aware of itself, at least locally. For a brief moment in cosmic time, matter organized itself into patterns complex enough to contemplate its own existence. That's extraordinary. It's fragile, it's precious, and it's enough. We don't need to spread across the galaxy to matter. We don't need to defeat the cosmic speed limit to have purpose. We exist. We're aware. We can reduce suffering and increase flourishing in our local pocket of space-time. Carl Sagan said it best, "The Earth is a very small stage in a vast cosmic arena. Think of the rivers of blood spilled by all those generals and emperors so that in glory and triumph they could become the momentary masters of a fraction of a dot. We're trapped, absolutely, fundamentally, inescapably trapped by the speed of light and the vastness of space. And that's the reality we have to accept. But acceptance doesn't mean giving up. It means directing our energy toward achievable goals, toward making life better on Earth, toward sustainable expansion within our solar system, toward understanding the universe through observation, even if we can't physically explore it. Our ancestors crossed oceans to explore the Earth. We've crossed space to reach the moon and send robots to other planets. Future generations might establish outposts throughout the solar system. But the stars? The stars are beyond us. The galaxy is beyond us. That's not pessimism, it's physics. So, we make the most of what we have, this one blue-green world, this tiny oasis in the cosmic desert. We appreciate it, we protect it, we thrive on it for as long as we can. Because in the end, the cosmic speed limit isn't a barrier to overcome, it's a fundamental feature of reality. The universe is vast beyond human comprehension. The distances are impossible. The energies required are astronomical. The timescales are inhuman. We're trapped in the solar system forever, not because we lack courage, not because we lack ambition, not because we lack technology. We're trapped because reality doesn't care about our dreams. And we have to learn to be okay with that. The cosmic speed limit, why we're trapped in the solar system forever. Thanks for watching.